Okay, so this is part 3 of our tutorial on our Loci visualization interactive app. We're going to cover different derived triangles on this module here, module number 3. Okay, so let's go to our app. Here's the default view. You got the elliptic billiard, the family of elliptic billiards. You're looking at the in-center, which is an elliptic locus. As we showed before, you can either change the triangle center that you're going to be looking at by clicking here. So I can go to the, for example, the barycenter or centroid. I can go to the circumcenter. I can go to the orthocenter. I can investigate and stop the simulation, investigate the type of conic, if this is a conic. So for example, the orthocenter is an ellipse. I can change the A over B of my elliptic billiard or of my generating ellipse. And I can do, for example, change the family of triangles. So I'm looking at the elliptic billiard family here, so I can change it to the homothetic family, for example, by clicking here. Then it turns out that the locus of the orthocenter in the homothetic case is also an ellipse. Okay, and then we can actually span all the way to 1000 here. So I can go to, for example, 444. What's point 444 have? What kind of locus does it have? And the homothetic pair, it has this locus, so I can go to 800, 898, and I'm going to get something that is self-intersected. Look at how interesting this is. So this is probably the first self-intersected locus we see, and we can analyze that. That's the homothetic. This is over the homothetic triangles. I can go back to the billiard triangles, and I can look at the locus of 898 and so forth and so on. So you can actually set things, the triangle center that you're going to be looking at from 1 all the way to 1000. Okay, so that gives you quite a bit of power. All right, so let me hit this reset UI thing here, and let's go back to our default thing. I want to talk about another sort of orthogonal concept on this video, which is the triangle family. Okay, sorry, the type of the derived triangle, not the triangle family. So what we call the family is billiard or homothetic, and there are other families on this menu here. But we're going to talk about the type of derived triangle. And when you're talking about the original triangle, we call that guy reference triangle. I have probably upwards of 30 different types of triangles that we can choose here, and they're classical derived triangles. For example, let's take the anti-complement triangle right here, anti-complement. So if I select anti-complement, I'm going to get my original family triangle here. And on top of it, I'm going to have a derived triangle. So the anti-complement triangle, I just remember it by memory, but you can always go to Math World. So if you go here, anti-complementary triangle, and you hit Google and you go to Math World, it's going to show you what the construction is. For the anti-complementary triangle, you start with a reference black triangle here. And then what you do is you draw sides. So you're going to take a parallel to side AB, and you're going to just draw it through C. And you're going to take a parallel of side AC and draw it through B, and then you're going to take a parallel of the last side BC and draw it through A, and you're going to get this blue triangle who has 4 times the area of the original one. Actually, the original one is the medial triangle, since these 3 vertices are going to lie on the midpoints of these 3 sides. And what this red circle is showing here is that the orthocenter of the anti-complementary triangle, the circumcenter of the anti-complementary triangle is the orthocenter of the original triangle. So there are all kinds of properties that you can talk about, but they're sort of beyond the scope of what we want to talk about here. Let's go back to our simulation. Okay. And oops, I lost it. So let's bring it back up. So I can go ahead and, instead of focusing on the original reference family, I can say I want to observe what's happening with the anti-complementary triangle of this family. So there it is. I'm drawing the anti-complementary triangle. It's this 4 times the area triangle of the original ones. And what I'm looking at right now is, let's stop that. I'm looking at the in-center, not of the reference family. Remember, the in-center of the reference family did this. Okay, this is the in-center of the reference family. But I'm looking at the locus of the in-center of this derived triangle, the anti-complementary. And it happens to be an ellipse as well. Okay, so that's a nice finding. Okay, so just as I computed what the anti-complementary triangle's in center is, I could, for example, want to look at the excentral triangle. Let's take the excentral triangle. That's another type of derived triangle. If you recall what the excentral triangle is, what you do is you're going to be drawing lines or the sides of the excentral triangles pass through each of the original vertices at directions that are perpendicular to the bisectors. Okay, so this is in many ways very much related to the geometry of the bisectors, therefore of the incenters, right? But you get this derived triangle here called the excentral triangle. Recall that its vertices lie at the so-called excenters of a triangle. All right, and now I'm looking at the apparently non-elliptic path or locus of the incenter of the excentral triangle. So it's non-elliptic. How do I know it's non-elliptic? Because there's no letter following this x1. If I move this guy to x2, I get the elliptic path of the centroid of the excenter. So this x2 is a centroid of this excenter. Let's move forward. I want to show you what happens. So the circumcenter of the excentral triangle, which is the B1 point, it's x40 of the original, has an elliptic locus. Let's keep going. Here's the orthocenter, also elliptic. Here is the 9-point circle of the excentral triangle. It has an elliptic path. Now we hit x6. Look at what happens. The locus of x6 is stationary at the center of the billiard. Now why is that? Okay, let's figure out why this is happening. Let's go here back to Math World, and I'm going to type here excentral triangle. And we're going to look at this cross-check table that is below every single one of these derived triangles after the properties. And it's going to say, oh, the symmedian point of the excentral triangle corresponds to the meeting point of the reference triangle. Now, we saw that in the elliptic billiard family, the meeting point of my three periodics was stationary at the billiard center. Since these 2 points are congruent, go back to the simulation, and you get that the symmedian point of the excentral triangle is stationary at the billiard center. Okay, so I can explore the symmedian, the locus of the symmedian point of the excentral triangle, for example, over the homothetic family. Here's a homothetic family. Well, the path of the x6 is nothing interesting, doesn't seem to be conic at all, and I can explore x5 and x4 and x3 and x2 and x1 for homosthetics over this derived triangle. So you feel free to just select, and by the way, let me show you guys a very cool feature here. You can always hit B box, and B box is going to reposition your simulation in such a way that you can see it better. With the mouse wheel, you can zoom out, and you can just drag and drop with your mouse, just clicking and dragging. That's just going to reposition the center of the simulation. So that's quite convenient. So you can start this again, and you can see, you know, perhaps a complete view of this whole thing like that. Okay. Okay. So for example, if I wanted to see the locus of x1 for the excentral and simultaneously see the locus of x1, I'm going to turn this thing on, for in the homothetic, so that they're both homothetic, but for the reference, so here I have excentral, I have reference, you're going to see the two paths simultaneously. So in the homothetic family, neither, so the locus of neither the reference x1 nor the excentral x1 are conics. Okay. Now, one thing that I did not, of course, you can go ahead and explore a bunch of these triangles here, and we have a whole list here. We have a list of about 30 plus triangles. They're all well known. A pretty interesting one is perhaps, let's talk about this one now, the Orthic Triangle. So let's go ahead and reset the UI. I can click here and reset the UI. And I'm going to set this guy here now to Orthic. Let's go to the Orthic Triangle. Orthic Triangle is quite a non-linear object. This was kind of an early observation we made about a year and a half ago. The locus of the Orthic is rather interesting. So what you're seeing here, this triangle here, this derived triangle, is the Orthic Triangle to the three periodics. Okay. Now there's a pretty interesting phenomenon that happens. The incenter of the Orthic Triangle is the orthocenter of a triangle if that triangle is acute. Okay. Now, if you recall the path of the orthocenter, let's go ahead and draw here. Xn, reference triangle, orthocenter. Here's the locus of the orthocenter of billiard 3 periodics. Okay. You can see that this is a pretty nice upright ellipse, right? Ellipse. So there's the path of the orthocenter. Is that x4? Okay, is that ellipse? Now, notice that there are 4 regions here. There are regions where the 3 periodics is obtuse and the x4 is outside. There are regions where the 3 periodic is acute, so that's going to happen on this sector here and on that sector there, and x4 lies inside of the 3 periodic. So you have these 2 arcs here, elliptic arcs, where the 3 periodics are obtuse, and 2 other elliptic arcs which lie inside of the elliptic billiard where 3 periodics are acute. So let's observe first of all, before we talk about the orthic, and I'm going to change the speed to slow. I'm obtuse here. My 3 periodics are obtuse. Now they're going to turn into acute triangles as soon as x4 enters the elliptic billiard. I'm acute, I'm acute, I'm acute. I become obtuse again, and so forth and so on. So I'm switching around, I'm flipping through these 2 states, okay, in an alternate fashion. Now, what is happening to the orthic? Here's the orthic triangle, and here's the incenter of the orthic. Now, this is a beautiful phenomenon. When the reference triangle is acute, the incenter of the orthic coincides with the orthocenter. So right now, the triangle is not acute. It is, this angle here is greater than 90 degrees. The reference triangle is obtuse. So x1 is actually stuck to the obtuse vertex. So there's a switching phenomenon when it comes to the incenter of the orthic triangle of a reference triangle. And there's 2 states. You are either nailed to the acute vertex, to the obtuse vertex, in case the triangle is obtuse, or you're congruent with the orthocenter in the case that the original triangle is acute. So look at what happens to the locus of x1 of the orthic. It's currently on the elliptic billiard, so it's executing a sector of the elliptic billiard. As soon as the triangle of reference becomes acute, it actually follows x4, and then it becomes stuck to the elliptic billiard again. It's actually switching between these 2 modes in an alternate fashion. Now, is this true, for example, for the homothetic pair? Let's go ahead and switch this to homothetic and homothetic. Well, let's see what happens. Right now, all my homothetic triangles seem to be acute, so the 2 loci are following each other. Actually, let me go back for a second to the billiard case, because I want to show you guys something. Depending on A over B, all my 3 periodics can be acute. So let's go ahead and reduce A over B. I'm going to reduce A over B such that the locus of x4 is completely inside the elliptic billiard. So all my 3 periodics right now are acute. This means that both the orthocenter of my 3 periodics and the incenter of my orthic triangle are congruent. Of course, this is branching. It branches into those 4 states as soon as you make your billiard eccentric enough so that now it contains, 3 periodic family contains both acute and obtuse triangles. Now when you go over to the homothetic pair, on both cases, let's see what happens. I'm all acute. Now as I increase, I get the same phenomenon. Check it out. If I go beyond a certain threshold, now my homothetic family contains both acute and obtuse triangles in such a way that I'm going to get this branching out phenomenon. Okay, so I hope that on this video you learned that you can use this particular menu here on each one of the channels and select a particular derived triangle, in this case the orthic, but you could have selected the excentral, the anti-complementary, the medial, and so many other triangles that are available through this menu. Okay, thank you.